Hello, everyone. The presentation is by Cameron Dombi, Rafael Angulo, Randy Harris, Cole Loving.
Reinforcement techniques, Cameron Dombi. So, what are the properties of traditional reinforcement, and how does it fit into the 3D structure model? And how does the alternative method of using synthetic fibers bolster tensile strength and reduce cracking? While implementing traditional reinforcement methods into 3D concrete, the reinforcement method that is used must be compatible with the printing material to ensure a strong bond. The printing material is also more precise than traditional methods, allowing for less waste of reinforcement materials. The challenges of using traditional reinforcement methods include, but are not limited to, the compatibility of the material, the layer adhesion, reinforcement layout design issues, corrosion, and the cost. One example of these fibers is the use of steel fibers, which are used to hold together concrete from cracking under load. So, how are synthetic fibers used as opposed to traditional methods? So, synthetic fibers greatly increase tensile strength and flexural strength when added to the mix. They also limit the width and the extent of shrinkage cracking by bridging across the cracks to prevent them from widening. And in conclusion here, fibers in 3D printing enhance the mechanical properties of printed structures, providing strength, crack resistance, and flexibility, while also offering opportunities for material efficiency and customization.
Rafael Angulo. What is the most widely used reinforcement technique for C3DP printed concrete structures and why? Introduction. Steel fiber reinforced concrete in 3D printing. 3D printing uses almost no rebar reinforcement as a traditional design. The extruded concrete paste used in this process has fibers and uses interlayer adhesion. In the upper right, you see an example of the pattern of the steel fibers inside a sample of poured 3D printing concrete. Steel fibers reinforce concrete by enhancing its tensile strength. In traditional concrete, which is strong in compression but weak in tension, the addition of the steel fibers helps distribute forces more effectively, resisting cracking and improving the overall durability and strength of the material. The fiber acts as a reinforcement to hold the concrete together, especially under conditions where tensile forces might cause it to crack. Flexural strength test. Flexural strength of SFRC is 20,000 to 30,000 psi and 3,000 to 7,000 psi for regular reinforced concrete. The modulus of rupture in SFRC is greater than 1,000 psi and 500 to 700 psi in regular reinforced concrete. Adhesion is very important in 3D printing. Steel fibers reinforced concrete has interlayer adhesion. Time left to dry may cause bad adhesion if left to dry too long. Steel fibers can enhance the capacity of 3D printed concrete structures in several ways. Structural integrity. The uniform distribution of steel fibers in 3D printed concrete enhances overall structure integrity. This is particularly valuable in complex and intricate designs where ensuring a consistent and strong material throughout the structure is essential. Crack control. Steel fibers help control and limit cracking in 3D printed structures. The layer by layer printing process can introduce weaknesses, and steel fibers mitigate this by acting as a mesh, restricting crack propagation and improving the durability of structures. Ductility. The addition of steel fibers can enhance the ductility of 3D printed concrete, allowing it to deform and absorb energy before failure. This is critical in applications where resilience to dynamic forces or deformations is important. Steel fibers play a similar role in improving mechanical properties of 3D printed concrete structures as they do in traditional concrete, contributing to increased strength, crack resistance, and overall performance. In conclusion, while these developments demonstrate progress, challenges exist, including the need for standardization, thorough material testing, and consideration of long-term durability. The evolution of 3D concrete printing material is likely to continue, driving the ongoing research and advancements in both concrete technology and additive manufacturing processes. This is definitely could be a disruptive technology for the future, but the advantages sometimes outweigh the disadvantages. Thank you.
Traditional concrete and 3D printed concrete share some of the same reinforcement techniques. Both use steel rebar and fiber additives into the mixture for structural strength. With the addition of the steel fibers or the glass fibers, this gives you an enhanced structural strength and durability with both types of concrete. Where 3D printed concrete is different, 3D printed concrete can utilize continuous feed rods. These continuous feed rods dispense either a steel or a plastic rod for added automation. The continuous feed rods are mounted just above the nozzle and laid out on the previous layer just inches away from the nozzle as it's laying down the current layer of concrete. The application of 3D printed concrete by nature is automated. Like traditional concrete, there is prep work to be done before the concrete can be dispensed. With traditional concrete, forms must be set up, and with 3D printed concrete, a layout program must be written. So two common methods of applying 3D printed concrete is with the use of a robotic arm or a gantry setup. One benefit of the gantry setup over the robotic arm is that typically you do not have to reposition the gantry setup many times to cover a large area. In small areas, a robotic arm may make more sense. Much like a 3D printer at home, 3D printed concrete uses an extruder setup. A typical extruder setup includes a pump unit, a concrete tank, a feeder screw, and a nozzle. The pump is used to pump the concrete through the system. The concrete tank acts as a hopper or a storage tank. The feeder screw moves the concrete from the concrete through the nozzle. The nozzle excretes the concrete into the layers that we see. The cost of concrete varies greatly for both traditional and 3D printed concrete. Like any new technology, and 3D printed concrete is no exception, the cost can be a barrier to use. The price alone of 3D printed concrete should not be the only factor to consider. Due diligence should be given to both the hard and soft cost of concrete. 3D printed concrete materials can be more expensive than traditional concrete. However, you should consider the cost of traditional concrete delivery transportation and the cost savings of 3D printed concrete. can have by avoiding delivery trucks. This may not make sense for small projects, but you may be able to take advantage of these cost savings with larger projects with larger economy of scale. The effectiveness of rebar in 3D printed concrete is similar to traditional concrete. In both traditional and 3D printed concrete, the addition of fibers help improve tensile strength and generally more durable concrete. Where 3D printed concrete differs in automation is with the application of reinforcement. With the use of continuous feed reels and different admixtures such as graphene for structural strength. As with anything in life, there's always going to be pros and cons. In traditional concrete, hand-laid rebar is a common selection for reinforcement. With the 3D printed concrete, you can use hand-laid rebar, but you will not have an efficiency advantage and typically be limited to only using a robotic arm. However, with the use of 3D printed concrete, you can gain an efficiency advantage over traditional concrete and rebar by the use of a continuous feed system that dispenses the reinforcement at the same time the concrete is being laid. This time I'll hand it over to Cole to discuss the existing challenges with current reinforcement techniques for 3D printed concrete.
Hello everyone, my name is Cole Loving, and today I'm going to be discussing some of the existing challenges with the current reinforcement techniques for C3DP. C3DP poses some challenges because there's multiple moving parts between the motors, pumps, and material, and everything must be perfectly synchronized. Trying to add reinforcement techniques into the mix is even more challenging. There are structural and strength-related factors such as workability and material properties, hardening time, mechanical properties, and durability properties that are important to consider before diving into the reinforcement of these materials. One of the most common challenges faced with C3DP is finding reliable reinforcement techniques. Reinforcement of C3DP is very challenging because traditional concrete reinforcement techniques do not work, since large steel reinforcements will block or interfere with extruding mechanisms. There have been many reinforcing techniques that have been tested. Some more common techniques that have been tested, such as inserting rebar, embedding wires, cables, nails, fiber reinforcement, have all helped to achieve significant structural improvements. On the right is an example of a horizontal steel bar being used as reinforcement. Now, while this technique might work for smaller scale projects, it should become more faulty as the scale goes up. Traditionally, large-scale concrete structures include the use of vertical and horizontal reinforcement for the most effective results. Though without the use of forms, this has been particularly challenging in C3DP. Both vertical and horizontal reinforcement techniques have been tested, though there is no tried and true method. Horizontal reinforcement techniques are the most common between the two since they have less interference with the printing mechanism. Horizontal methods include inserting rebar or mesh either between the printed layers or within the printed strip. Also, a common method is the use of steel fibers within the printed strip. There are currently not many effective vertical reinforcement techniques, though inserting small vertical nails or rebar while printing is an option. In the image below, there are a few examples of these horizontal and vertical techniques. We can see, on the bottom, extruded short fibers, a mesh between layers, rebar between layers, embedded long reinforcement between layers and within the printed strip. On the top there, we see the nozzle unit. It's moving to the right. And in the text box to the right, it states, reinforcement cannot be higher than this line to avoid blocking the nozzle. This is what I was referring to when I was talking about the interference with the mechanism. Though, you can still insert the small nails or rebar vertically. While many reinforcement methods have proved to significantly increase the strength of the structure, most techniques do have their downsides. Some of these downsides include having to manually insert the reinforcement or to have an outside mechanism that is required to assist with the placing of the reinforcement. Manual placement of the reinforcement takes time, and also it can disrupt the displacement of the cement paste, leading to further structural issues. It was also found that when inserting wire, cable, or rebar after the cement printing, this created voids within the concrete that weakened the overall structure. As you can see on the bottom right, the insertion of rebar or nails created voids. Even as small as they are, this can have effects on the structure's stability. Another challenge that is found with many of the reinforcement techniques for C3DP is the limit of the structure's complexity. Structures built by C3DP can only be so complex due to the machine's lack of maneuverability, reinforcement, and strength. And a newer, less common method referred to as contour crafting allows for more strength and vertical reinforcement. In this method, the gantry or robotic arm will build the layers in a hollow shell where vertical and horizontal rebar can be placed after it is built. This will act as a sort of formwork where then you can cast the concrete. I can see why this method isn't ideal due to the fact that cast in place using wood forms would be easier and quicker. Another is being used by a Chinese building company using steel wire mesh. This company installs the wire mesh beforehand, and with the use of custom printing nozzles on either side, it sandwiches the mesh within the concrete layers as shown in the picture below. More strategies will need to be tested and developed before a proven reinforcement method is available.